Okay, we are now going to have a fourth and final lecture by Tomoki, which is continuing his previous interesting discussion about the applications of cluster patterns.
Thank you. Okay, so let me continue my discussion on dilogarithm identity arising from a cluster algebra context. And so I recall the things which I did in my last lecture. So we introduced two kinds of dilogarithm function. First is called Euler dilogarithm, which is defined by originally power series formula, but also have the following integral expression. And to avoid the multivariateness of analytic continuation, we concentrate on the line, real line, which is smaller than 1. Yeah. And there is a brother of this Euler dialogue, which is called Rogers dilogarithm. You can define two ways. First, one is it is light as Lx, and sometimes called Rogers L function. And first, it is integral expression which symmetrizes this integral in the following manner. And once again, due to the multivariateness of x 0, 1, and 0, we only limit my attention in this real segments. But for some application, you consider it as an analytic function on complex plane by considering the multivariateness. And this quickly can be integrated out, and which gives you another alternative definition of L function using Rogers Euler dialogue and ordinary logarithm. So essentially, this is two functions are the same up to this elementary function. Yes. And I didn't mention, but maybe today I want to use the following expression. So I give, in addition, also, suppose you put minus x here, then of course you have minus x here. But you may want to cancel this minus a little bit annoying. So by changing the integrate variable with minus sign, then you can absorb this minus sign by change of sign, and these sign cancels out. So we still have this one, but log term becomes 1 plus y. So this is another expression, but in this case, x is greater than minus 1. Okay, so this is a little bit additional information which I want to use. And how it was related to cluster algebra, the situation as follows. We consider Earth sequence mutation. Of YCs with coefficients P, semi-field is taken as R plus, yeah? Real positive numbers. Yeah? So it looks like B. So we set the initial one to be B0, Y0, and make a mutation at K0's direction. You get something here. So this is considered as a parameter also regarded as a discrete time development, and K1, and so on. And repeat this, say, KT times starting from 0. So then the last one would be as follows. Yeah. And I call this sequence to be a star. And suppose this sequence, suppose that this sequence star is sigma periodic, where sigma is a permutation of, say, 1 to n, where n is a rank of this YCs, namely the last one, last seed, is obtained from first one by just changing all the indices of matrix and y variable by this permutation. Yeah. So particularly, it can be taken as identity. So it's a really ordinary period, but we somehow consider a partial period to accept several cases. So anyway, then we have the following dilogarithm identity. Let's call this di, which has the following form. So it's a summation over those each step, starting from 0 to t minus 1, and you sum up some special value of Rogers dilogarithm. Say for each time t, you pick up a special component of yt corresponding to exactly the one which you will hit the mutation. And you sum up with some integer weight where d is diagonal matrix, which is a common symmetrizer of this skew-symmetrizable matrix. Yeah, common skew-symmetrizer. Of those exchange matrices. Yeah. Then the claim is that so this is considered as a function of your initial choice of the YCs, which is nth power of its real positive integers. Yeah. And others are completely uniquely determined by the mutation. Yeah. So it is a function of your by the function, by the variables. But the claim is it is a constant. So it's with respect to the choice of your initial value. So in other words, this is a functional. It gives you a functional equation of this n variable if you rewrite everything as a function, rational function of your initial variables. Okay, so that was the dilogarithm identity. And last time I showed that for a particular example of type A2 and A1 and A2, it reduced to the classic Euler and Abel's identity of dilogarithm. And important fact is you use Rogers dilogarithm here, and the expression becomes very simple. If you use Euler dialog, you can just plug in this expression. Well, still we have a functional identity, but we have this a little bit annoying term. The fact is Rogers dialog cancel out this term if you write it in an Euler dialog. And after that, it becomes really needful. Yeah. And I will explain why it is so. But anyway, last time I briefly mentioned the possible proof of these things, and I repeat, but more kind of precisely. So I write some table like this. So far, I have 3 proofs of this important identity. And the method, first one is an algebraic method. This is my first proof, and it's kind of a straightforward proof. And so algebraic means I only use mutation formula and also separation formula, but everything is a manipulation of algebra. And this is a proof. So let's say, suppose it is mathematically rigorous, of course it is, yes, it is proof. But there is some disadvantage of this one. So this proof, which I don't explain you at all, I'm sorry, but it shows that right-hand side is actually is constant, is proven algebraically, but this proof really does not explain why, first of all, Rogers dialogue appear here. If you anticipate this one and you just make a derivation of this one, it end up with some algebraic relation, and you can prove that this is solved by the condition of this periodicity. So while dialogue, this proof does not give any insight at all. Yeah. So it's good that it is true, but still we don't know why this is true, in a sense, right? And so for me, it was unsatisfactory. And next, I consider a different approach. So using a quantum version, quantum version of this. So everything can be quantized. This is due to Fock and Goncharov, and you consider a non-commutative variable, y variable, and we consider quantum cluster algebra across quantum cluster patterns, and you can replace these things by so-called quantum dilogarithm due to Faddeev. And you can then take the classical limit of that things, and you obtain this. That's good, but one disadvantage is rigorousness is lost, because we have to use semi-classical analysis and sample point approximation. To justify it, you have to really have really it's a third point, but we don't really know from just the third point equation. Those things are very difficult to discuss. So rigorous is somehow up to the level of ordinary mathematical physics method. And also, this somehow explains why this function appears as a limit of a quantum dilogarithm function. But still, there is some problem. Namely, if you take the classical limit of quantum dilogarithm, what you obtained is actually Euler dilogarithm. And we have some extra term, and we can clean up these things and summarize it as Rogers dialogue. And so the Rogers dialogue appear after some calculation, which does not really explain why it can be summarized in that way. So it is not completely satisfactory. So I continue to consider this problem, and finally I end up with the following approach. It is, I would call, classical dynamics approach. Classical dynamics. And the good thing is this uses some physics idea, but nevertheless everything is rigorous. So it gives a mathematical proof. And also it clearly why dilogarithms, especially this in this form of Rogers dilogarithms, appear from cluster algebra. So it explains the intrinsic meaning of this identity. Yeah. So this is also good. And of course, so even this is so. There is no best proof for the method of proof. I mean, everything is complementary to each other. It shows some aspect, and it shows some other aspect. But today, especially, I want to explain this one, because it really gives you why this means in the point of view of cluster algebra. It's most clear. And this is based on the work of Michel Gechtmann and myself and Dylan Ruppel, which is published in last year. Okay, so this is what I'm going to explain you today. Where I this one? I explained already, but I'm interested in why did this function and this form appear? Ah, it's only for Japan. I see. It's in between. It's in between yes and no. Ah, okay. I thought it is a worldwide idea, but thank you very much for asking. So now remember the Japanese use this as a in between. Not yes, no, not no. Yeah, okay. Okay, it's really refreshing to know that. Anyhow, so where else? So, but before that, why classical dynamics appears? It's obvious. I mean, so I recall that this is a regular tree graph which sees a seat, and in cluster algebra you consider all this big graph, but you can, for example, in this kind of sequence of mutation, you particularly choose your initial point, and you choose some direction and next direction, and so on. So you have some one-dimensional subgraph of this one, and obviously this development, then the mutation as a rational transformation is considered as a discrete. Dynamical system, yeah. And my idea is to apply standard classical dynamical concept like Hamiltonian and Lagrangian to this discrete dynamical system. Then presently this identity naturally appears. That's I'm going to explain in the rest of my time. Okay. Any more questions about the symbol? It's okay. Okay. So. I only have two sections, and first I explain what is Hamiltonian in the context of this sequence of mutation. Yes. So today, I assume from now on, yeah, from now on, yeah. We assume this B matrix B appearing anywhere is skew-symmetric. Yeah. Just for simplicity. Today, my talk, I simplify many things just for technical, to avoid technical complete, just for simplicity. Yeah. So, for example, you don't need this term, but everything, including the general case, is written in my paper. So, okay, and so we start recall you y seed in coefficients in a semi-field P R plus is something we are considering to discuss this one. Yeah? But sometimes we do this trick, so every time we may consider some, you can replace this universal, say, okay, so it's some confliction, so BBT, with some it sit in some semi-field, universal semi-field of your initial variable. You can set it, and then after that you can specialize to this real positive numbers, yeah, by specialization. So we do this two way of thinking when it is necessary. Anyway, basically we want to consider this, and I just write once again, yeah, mutation formula of this y variable, which is important. So mutation at k equal 1 to n, and you when you make a okay, so now I really don't need it, don't want to this, and so maybe I put 0 somewhere here. So anyhow, mutation direction k of your y seed. So B matrix is as usual, so I skip, and let me write this because it is important in my talk. So B prime I is written as when I is k, and when it is not, then we have some formula. And we somehow replace ordinary this O plus symbol for just ordinary plus because there is no you can identify it with addition of real numbers or rational functions. Okay, so this is a formula I have wrote. Maybe this is my third time to wrote it. But anyway, now let's take a close look at this formula and consider its meaning. And before doing, first I point out the following important fact. So I somehow regret, but I put a little bit space here. So please do that. And I will put epsilon here. Where epsilon is plus or minus. Yeah. And the first comment is that this formula is independent. This is independent. So this one is independent of the choice of epsilon, whether it is plus or minus. It exactly gives you the same number. So you just manipulate this symbol and then you end up with the same. So there are two alternative expressions. And this redundancy is important. Anyhow, so what is a canonical choice of epsilon? There is a canonical choice. So the canonical choice is as follows of this sign. So to have some choice, you first fix after fixing. Yeah. Your initial point T0 in your tree graph. Yeah. Then we can consider the notion of tropical sign. I explained this. So starting from your initial variable here, everything. If you tropicalize that transformation, then the exponents is a positive or negative. There is no mixture. That I call it a tropical sign, and it depends on your choice of T0. But for my purpose, it's just okay to fix some point. Then we take this as say it depends on the which component of your y variable, y and yn. So k is a case tropical sign, and we choose this tropical sign. Yeah, this is a tropical sign of your y variable here, yk. Yeah, and then after setting this, we have a nice statement. So. First, I said this expression is independent of choice of epsilon. But if you, how to say, separate these things, of course, it's a different things. So point is, product is does not depend, but if you separate, it's different. So when you separate it, you need to choose some sign, and both are possible, but especially this choice give a nice meaning. So nice meaning means this part is exactly becomes what is called tropical transformation, which is just when you specialize to this tropical semi-field, this transformation is available with this choice of sign. So this is considered as a tropical part. Last time I mentioned this when we talk about the separation formula, but now I'm talking at the level of mutation. Yeah. And you know, there is some hidden multiplication of number 1 here. And number 1 is actually a part of this formula. When you set i's or k's, then b, k, k always 0 due to skew-symmetric property or skew-symmetrizable property. So this is a part of the same formula, and so this is just multiplication, this one. And this transformation I called non-tropical one. Non-tropical, maybe tropical transformation, yeah? Let's call this tropical transformation. And let's call non-tropical transformation. And so what I said is mutation is regarded as a composition of 2 transformations. One is non-tropical one. Then after that, you make a tropical transformation. And this expression has a very intrinsic meaning from the point of view of this classical dynamics point of view, which I'm going to explain. Okay. Now, to discuss everything, now we really need to introduce this tropical sign. But because this is just 1 hour lecture, and I want to skip many complicated things. So let me assume the following simplicity. So below, pretend that all the tropical sign which encountered during the mutation is 1, plus 1, yeah? Just for simplicity during the mutation. During our choice of sequence of mutations, for simplicity, yeah, just for simplicity, Then we somehow get rid of writing these things for every formula, and that makes my presentation easier. And for you, for first time, it's easy to understand. And of course, once again, every detail is given here, so including this one. So anyhow, so what I mean is now we separate these things, just consider it as a plus sign. Okay. So now I'm describing Hamiltonian picture of this mutation. And this was first stated by Fock and Goncharov, just by sentence, not by any formula. It is in a series of papers, there is just one small sentence which they mentioned about in the following one. So Euler dilogarithm with this minus sign, we say k, is Hamiltonian. Of mutation. I mean, this formula. It was not clear to me what this means at the first moment, and I somehow start my business to understand this one. So now I'm going to explain, need some classical dynamics notion. So Hamiltonian is together used to formulate classical dynamics together with so-called Poisson bracket. So I need to introduce Poisson bracket to explain in this vector. And there is actually a canonical one which is associated to each seed. Associated with, say, y seed, P of y. And that is, so when we talk about this Poisson bracket, y is the value of real positive number, or it's just a variable which take a value in real positive numbers. Anyway, the bracket is defined just by the following way. And I recall that this is a skew-symmetric, for simplicity, this setting, so skew-symmetric. So it gives you a skew-symmetric form, but with this things. Okay, so this one was first introduced by my joint author Hitman and Misha Shapiro and Alec Weinstein on a very early stage of cluster algebra, where cluster algebra was not popular at the time at all. And this has a very nice property under mutation, namely it is invariant under the mutation. Which means that if you define the same quantity for this, if you define this for your variable, and then when you define this prime variable by this mutation, then they satisfy the same Poisson bracket, but everything is replaced by prime variables. So it is a kind of canonical one, and so that we can insist if you want to everything at a particular coordinate, and other things is considered as tropical. Okay, and mutation, but also I want to mention that invariant under the tropical mutation, tropical transformation. Yeah. So this part, it's actually more easy to do this, and if you use this part, then the mutation formula exactly gives you the B matrix mutation formula. So invariant condition is equivalent to say that B matrix mutate as our standard exchange matrix. So in a sense, this property explain why B matrix have to be mutated like that. Yeah. So this is one thing I want to mention. And this Poisson bracket, now we consider a Hamiltonian. Yeah. So maybe I erase this portion, but please kind of remember this dilogarithm form of the dilogarithm identity, which I will use. Explain it. I'm going to explain it. Okay. So maybe I write here. Now I introduce Hamiltonian for this mutation mu k, so I call this Hamiltonian at k, yeah, for k's direction, which is according to Fock and Goncharov, it is given by Euler dilogarithm with this minus sign. That is what this paper says in one sentence. And I'm going to explain this, having this Poisson bracket. Okay, so this is just a definition. So this is a function of y, but it only depends on actually a case variable. And what is the usage of a Hamiltonian in classical terms? It gives you an equation motion, or equation of motion. All I use is a very standard, what I say, of standard classical dynamics, no quantum mechanics or no quantum field theory, just ordinary standard classical dynamics. So usually, so in this picture, why those variables will change according to the time, yeah? And time derivation is written in this dot symbol. Yeah, so it is a standard notation for a classical dynamics. So it means if you consider it as a time-dependent variable, it is a derivation to this variable. Yeah, and so is given by the Poisson bracket with a Hamiltonian is a definition of the Hamiltonian. HKI. So let's calculate together this simple thing. So this is a function of y, by the way. So maybe it's better to write as a function of y. But in reality, it only depends on k, but nevertheless. Then according to the simple the formula of a Poisson bracket, you can do it using the derivation of the chain rule. But this one actually only depends on variable. So actually this is the ordinary derivative, but somehow just showing that this is a chain part of the chain rule. So I somehow write this symbol. So this is coming from the derivation property of Hamiltonian Poisson bracket. So what is this? We just phase-free calculate. So I recall you that this one is actually even by maybe y is a little bit so in this case maybe write integration value x instead of the opposite one last time I wrote it. So you just remove this integral and it gives you the following things, yeah. So but put yk here. This coming from the derivation, this one. On the other hand, this one, by definition, I use this Poisson bracket. So bki, yk, yi. Only one good thing happened here, so namely, you can delete this one. Okay, so now it's good to put everything on the shoulder of inside logarithm. So I write this. Oh, it's not everything, but I somehow put yn here, and I put the rest things in this form. So now you recognize that it's very closer to these things, but to complete this, we have to remove this logarithm part. This is done by integration. Namely, so before going on, we note that in particular of this Hamiltonian dynamics, so if you put I to be k, k is the direction of the mutation which is chosen for this variable, then you substitute k here, but bkk is 0. Due to skew-symmetric property. So this quantity vanishes. So it is 0. See? Due to b, kk is 0. Yeah. So this is a part of the formula, but I especially mentioned this. It means bk is a constant. Yeah. So so this one is a constant. Constant. Yeah. So yk is constant. So then once again, we look into this formula, but this portion is constant, yeah? Because yk is constant, I mean, along the time. So it's just a constant, so derivation is just gives you a constant. So you can integrate from time to 0 to 1, it is called time 1 flow in a classical. So this is just give you a velocity, but you can integrate into from 0 to 1, it is called time 1 map in the dynamical system. So time 1 flow, yeah, time 1 flow, I would say. So it means y starting from the value y1, this portion is just replaced by exponentials. Because derivation, then this gives you this formula. So the conclusion of my discussion it gives you exactly the non-tropical transformation. Probably I call it the non-tropical part, but anyway, it's okay. Non-tropical transformation of mutation, yeah. And that is Fock and Goncharov a lot in this simple sentence. Now we understand what it means. You ask me the calculation around here. So you want to ask me how I get this from this, or what is your? Yeah. So generally, if you have two functions of something like this, you have to calculate those things. But in this case, it's quite simplified because y variable itself is already y, and this is only dependent on the single variable yk. This is a definition of our Poisson bracket. Yeah, so we just apply this here. Yeah, so this is our formula. Yeah. Okay, so let me continue. Where's this? Oh, it was okay here. So far now you may ask, what is this tropical transformation means? It is, I would say, it is just a change of coordinate. So there is no special meaning in dynamics. It just gives a coordinate transformation. So somehow we have the following picture. It's a very schematic one, but your word choosing the first variable, y plus n with variable, you have some original variable, y. And you consider time development of those variables according to this equation motion, which is actually given by this formula. Yes. And so somehow we write schematically in this way. So this is given by, correspond to non-tropical plot or mutation. On the other hand, so mutation is the composition of this one first, then this one second, and this we just regard to another chart of the same things, but in it is related by just tropical transformation. Only this part we somehow decomposed into this picture. Yes. And now, so what is really going on? So this is the time of our universe is actually this one, but this just gives our coordinate of describing this one. So this is the picture of our Hamiltonian. Yeah. So question, this is good. So it means quantum, so Euler diagram is already built into cluster algebra very directly. Yeah. So this form, you notice that 1 plus y is actually exactly correspond to this function. This portion? Sorry, this portion. Just the very simplest non-trivial binomial is in fact appear here. And so those two things are connected by this simple observation. So anyhow, let me go on. So the question is, okay, that is good. But from this point of view, so my next question is, can we derive our dilogarithm identity from this picture? And if it is so, then the question is, okay, so Hamiltonian, we have Euler dilogarithm. No Rogers dilogarithm. But our last result is somehow Rogers dilogarithm is preferred. Why this change happens? Yeah. So why the Rogers dilogarithm, yeah, Lx, instead of Euler dilogarithm? Yeah. It's might be technical question, but it really concerns me a lot. And now, to answer this question, we have the following crucial observation. First, how these two functions are related. There are two ways to relate. So it is already mentioned that the L function is related by Euler dilogarithm by this simple transformation. Yeah. And this is a well-known one. Yeah, so this is a well-known standard. How to say standard. You can see it every textbook or Wikipedia, whatever. You will find this. How to say relation between two functions. But this is not a good one, I would say. And instead, we have another less well-known identity connecting these two functions, and that is important for well-known. Less well-known identity. That is the following form. And this one now, it's a good form. It's exactly the form where dilogarithm identity is written. And this one is related to one, we have minus sign here, and Li2, and we have minus sign here. This is good because in this picture, we have plus here, so we have plus here, so this minus is somewhat very crucial. But this one. And minus 1/2 log x, and this one becomes plus. And this is identity. You can easily prove it just by taking the derivative of both hand side. And it's a good exercise to prove this one. And I mentioned that, now I want to say that this formula really already explained why this function is important. And so you consider this as a transformation of this function to this function. And from my context, it was a Hamiltonian. What is this? Yeah. And I'm going to explain you that this is a Lagrangian. Yeah. Another way to formulate dynamics, Lagrangian. And then this transformation is called Legendre transformation in the sense of classical dynamics. I don't have a... Okay, let me write just boldly on the top of this Legendre transformation. Yeah. Once you recognize this kind of picture, then everything, now the dilogarithm identity becomes clearly understood. So in the rest of my talk, I explain Lagrangian and how this picture really gives you a true understanding of the dilogarithm identity. I have 22 minutes to go on. So the last section of my talk is now I transfer to Lagrangian. And to do that, actually, usually physics, for physics, you start from Lagrangian and transform to Hamiltonian. But you can come back to the other way. So we start from this one, so we had to come back. But in any case, this transformation, called Legendre transformation, is usually defined using what is called canonical variables. With respect to your Poisson bracket, but this is not canonical at all. I mean, canonical means that this is a kind of a delta ij something. So I'm going to introduce canonical variable. It's not canonical in the sense of mathematics at all, but it's a very standard terminology coming back to 18th century, 19th century variable. So it's a coordinates in a so-called phase space coordinates. So it is now degree of freedom is doubled to n. And it is a pair of n tuple of variable. In my context, usually it is x and p, but x is for cluster variables, so somehow I changed to ui and pi. And together they are the coordinate of these things. And canonical variable means a Poisson bracket satisfies in my convention in the following way. So this is delta is a canonical delta, and UI and PI are 0. Yeah, and this is the definition. So let's consider just such variable satisfying this thing. So you just consider it as a definition of this Poisson bracket for the function of this U and P function of U and P. Now I want to cooperate with these things, and you can actually construct this y variable from this UI and PI in the following simple formula. So it's we define through from this and using this given skew-symmetric matrix entry Bij, but this time I used as in this setting like this. Yeah, we just define for any skew-symmetric matrix, and then it is easy exercise that those variable indeed satisfy that form, but with a little bit different normalization twice. So now we somehow embedded this y variable in this canonical coordinate system. And you can remove this factor by just considering square root of 1, but it's somewhat annoying. So just keep this one. Then we keep to keep these things. You have to divide this by 1/2 somehow. So we now re-normalize our Hamiltonian according to this setting that Hamiltonian h of k is 1/2. I put here, but the rest will be the same. So it is a Euler dialogue of minus yk. So this is a function of actually u and p through this function. Yeah. So you have a Hamiltonian for this so-called phase space. And having this picture, you define Lagrangian by the standard Legendre transformation. Namely, I put this so-called quotation mark by which I explain later. But anyway, Lagrangian Lk, maybe L of k. To distinguish it as a letter of Rogers dialogue, I just use curly L here, which is it is written in any textbook of classical mechanics. So it is given by the following. So HK, yeah. Like this, yeah. So it's good. Now, a little bit unpleasant part happens, and I somehow don't explain very much. But unfortunately, this Hamiltonian is too simple from the point of view. Yes, yes. Di, where did here? I consider skew-symmetric. Oh, di. Pi. P is here, which now we consider it all depends on the time. And this is a time derivation of pi dot. So you consider a system of UP which developed by this Hamiltonian in a phase space they are moving. So you can consider at a special slice of time you have derivative, time derivative of this pi. Is that your question? Okay. So anyway, that is a transformation which is momentum. P is called momentum in general. Yes, with respect to the variable x. I don't hear your question, but the probably answer is yes, right? No? Lagrangian transform. Yeah. Yeah. You usually, maybe you starting from Lagrangian, you do it in opposite way. But I mean, in a suitable identification of these variables through Lagrangian equation and those things, yeah. Sorry, but we just accept this as a definition of these things, yeah. And now I come back to the unpleasant part. Is this is too simple, so that it is called what is called singular Hamiltonian. Technically speaking, it's not a good one. Then this transformation is actually causes a lot of problems. So namely, one can actually do not have a Lagrangian description due to this singularity. So generally, if it is non-singular, then the two system becomes equivalent. But nevertheless, let's forget these details. Just accept this kind of standard notation. And everything will be cured very neatly, but I don't have time to explain it. So just believe in me, and everything is written in a paper. Okay, so that's why I call this put a little bit caution. So because you don't really use it as ordinary Lagrangians, and this system has some discrepancy. But okay, let's leave this out of my question. And also now we have a little bit unpleasant part, but this portion can be calculated in a particular phase space, so-called. So in a subspace, subphase space, in subphase space, it's also some technical detail, but I concerned, so I write it, but you don't have to care it actually. So such that we have some half dimension of this whole phase space, which satisfies such constraint. Yeah. And in that case, this quantity can be written in a following manner. So that is the meaning of this quotation. And but let me write the conclusion. This part is just simply here. So what I said is, in a particular subphase space, this portion can be calculated in a following manner. And nice thing is this subspace is preserved in Hamiltonian, by Hamiltonian. So you can concentrate on this small phase space that this identity holds. Well, have you ever look this combination? Yes, of course, it is written there with multiplication of 1/2, right? So what I said is, then right-hand side is exactly 1/2 of Rogers' dilogarithm function with this combination. That's now very close to our dilogarithm identity. So this part is considered as a Lagrangian of our Hamiltonian system. Now, so to complete our picture, what we are going to consider is so-called action integral of this Lagrangian. So I write some schematic picture according to our sequence of mutation. So we somehow write the following scheme. And so this is a time axis, and starting from 0, 1, and say t. So each segment corresponds to the one-time mutation of ordinary y variable. And we somehow write y variable as a dynamical variable in the setting. And so this is your initial variable. It specifies some point in this space, in a y space. And then this things is developed according to this Hamiltonian things here. And as I mentioned, this can be transformed by tropical transformation to another coordinate called yn. And so this is for k0 direction, this is ky direction, and so on. And you repeat. And so on. And periodicity actually means the coordinate here and the coordinate is the same. It is a periodicity condition. Yeah. And anyhow, so in that picture, those transformation is just an artificial one. So it's necessary to describe these things. And really what happened is just here. This is a dynamics part, and this is just a change of coordinate. And along this dynamics from 0 to t, we consider what is called action integral. So it is S, it is called symbol S, which is nothing but the integration of Lagrangian at each time. So it's very simply written in this following way. And this choiceable Lagrangian depend on the segment, so K0, K1, and so on. And each time you choose a particular direction. So it is a piecewise constant Lagrangian for those things. So, and Lagrangian itself is also a function of only one variable, yk. And so, furthermore, I said that recall y dot k is 0, written somewhere here. Yes. So y is just constant. So it means Lagrangian is constant along the contour. So it follows that first observation, important observation is this integration, seemingly integration, is just the addition of constant Lagrangian at each segment. So it just gives you 0 to time t minus 1, and its value is 1/2. And here we choose those variable at a special direction, which is exactly chosen at k of t in this each local each coordinate at time. So you have seen this before. So this is exactly, so except for this 1/2, this is the left-hand side of dilogarithm identity itself. So what I said is dilogarithm identity, left-hand side is nothing but the action integral of the associated dynamical system. Okay, so this is okay, now to go to the last point, I want to say that this does not depend on the choice of your initial value. That is the dilogarithm identity. So we are almost done, and what we remain to show is the following claim. So claim is that if the period, this sequence of mutation coming to this is somehow up to sigma mutation periodic. So suppose it is a sigma periodic. Then this constant action integral as is actually independent of your choice of initial value. That is the content of dilogarithm identity. And we give a proof of, at least give an outline of proof, almost proof, but some detail is necessary, and which is given our paper. So conceptually, this is well-known, is a variation, well-known fact in classical dynamics. Namely, it's exactly coming from finite time version of famous Natal's theorem, yeah, in classical dynamics. So everybody in this room respect her very much, right? So Natal's theorem. Natal's. So first give some picture. So we somehow can write this space in a various place where, for example, you can write in Y space, but maybe you can also write in a U space. And U space U coordinate are developed by some, generally speaking, yeah, it's some trajectory according to this Hamiltonian picture. And we somehow want to change the initial point. Then contour changes. Where so t, this is time zero slice of the space and space time, and this is a time final time slice of the space time, and this is in between, somewhere in between. Yeah, and so having this integral picture makes things very convenient, even though it is a finite sum. Yeah, so that is my point. And we want to calculate the difference of this action along two contours, and we want to say that the difference is zero. That is this statement, right? And so to do that, we usually consider a very small change of contour and how your Lagrangian changes. In fact, the part of it gives you the Natal's theorem. So we start from Natal's theorem. Recall you how to this can be derived in a very concise way. So suppose for simplicity, so UI only I variable goes to be shifted by something. Yeah. So this shows just deviation of this variation of this variable. Only for for each I, suppose you things change. Then what your Lagrangian, which is an integrand of this one, changes. This is a very Lagrangian is actually considered as a function of u variable and its derivative, and it is also true for this context. So we have the following thing. So first we calculate these things, and also you have the other part coming from you dot variables. Yeah. It is a standard calculation, and first things I want to mention is it is so-called what is called equation motion, exactly telling this contour in terms of Lagrangian picture. Is the equality that this one can be rewritten as follows. So these things should coincide. And then this one is the same things, and this one is a derivative of this variation. So it's summarized into the following neat form: delta u dot I, delta u dot I. Yeah, it's the total becomes total derivative. And so once again. Equation motion by the identification of Legendre transformations. So these are regarded as dot UI, so momentum variables. Okay, so everything is good, and just temporarily write this as I, this quantity to be I, and then so this gives you how the variation of this one is. Given by the derivation of right-handed. And suppose, so in particularly, this is zero, so we have actually higher terms, but up to the order of this variation, then which is equivalent to the right-hand side vanishes. Yeah. So integral of t vanishes. So I is vanished, and sometimes it is called I is integral motion. I is an integral motion, conserved quantity. And this is what Noether's theorem tells you. But in our case, we are interested in this variation of action itself. Yeah. Yes. So, but it's just in seconds. So beep will be anticipated. Okay. Thank you for the final code. And I very soon finish. So, what is the finite time? Time version. It is just integration of this one to time derivative. So, namely, how these things changes when you shift this contour a little, then it is just integration of these things along the contour. Eh? But this one is already calculated. Here, it becomes a total derivative of something. So it's just integrated. Yeah. I to be 0 to t. Yes, and so it means this quantity is 0 up to first order of your change if and only if this quantity, which I wrote I, is periodic, yeah? Or I would say, yes, I is periodic. Now you see how periodicity enter into the business at the very last moment. You know, our assumption is here. So actually, this one is guaranteed by the following sequence of argument. So our periodic, our assumption is the following. From this, actually comparing the mutation formula of y variable and u variable, you can actually claim that u and p are also sigma periodic. Here we need some technical part of cluster algebra where, for example, we need the tropicalization theorem and so on. Yeah. But once this is periodic, then everything is periodic as a function of P. Are you asking? Okay. And we make a summation which kills you this sigma things because it's a change of indices. So final term disappears. So summation is periodic. So we have derivation is 0 for any choice of movement. Any function is periodic because u and p are periodic at here and here. So it means derivative of s is 0 for any direction. It means s is constant. Yeah. So s is constant. And this ends the proof of dilogarithm identity and also my lecture. Thank you very much. Symmetrizable case? Yeah, it's exactly the same. We just have some weight for several parts. Yes, yes. With adding this, so you know, D is for make things skew-symmetric, right? So make this skew-symmetric. We use that for the definition of Poisson bracket. Yeah, yeah. Becomes just yes, 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 yes. Yes. Yes, yes, of course, yes. Yes, 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 of course, yeah. Yes, yeah, everything is. You just put D and also tropical sign for everywhere, but I skipped it, yeah.
Thank you very much. Any more questions?
You're asking me about where? Just below. This one? Well, forget about, okay. Thank you very much, yeah. Yes. You know, in a quantum picture, it is so. It is described as a quantum system. So it is a classical limit of it. But you know, going back from quantum to classical is really tricky business. And where Legendre transformation naturally appear when you do that. So not directly obtain Euler dialogue, but Rogers dialogue appear. Because Lagrangian is responsible for this, how to say, path integral picture of quantum dynamics.
Any more questions?
Yeah? Yeah? Yeah. I don't know. I mean, this is actually part of like geometry, but well, I'm not quite sure how far I can go. But through the derivation rule? Yeah. That's right. Yeah. That's right. Yeah. It's possible for any smooth function. Well, this proof is beyond my lecture, but it is somehow standard in mathematical, classical, dynamical text. Yeah.
Any more questions? Okay, no more questions. Let's thank the speaker again.